Friends, today we are going to discuss the different parts of turbines. The picture depicts in the screen is the rotor assembly of a turbine. You see, this is the turbine, this is the turbine. This is the journal portion, front journal bearing. This one is the rear journal bearing. These are the rotor blades. These are the rotor blades. You see, this is called the disc. This one is called the disc, and this is the blade. Blade is mounted on the disc, and this is the coupling hub of rear side of the turbine, and this is the thrust collar, and this is the coupling hub of the high pressure side of the turbine and turbine rotor assembly. And these are the two ceilings. We have to put the two ceilings, nylon rope ceilings we can use, so that there should not be, if you use metal ceiling, then there is a chances that there may generate a scoring mark here and here. But if you use a nylon ceiling, there it is there is no chance the shaft or rotor will damage. And not only that, it will put in such a position that rotor will be always lifted in a horizontal condition. So this is the parts of a rotor turbine. This is, you see that this is the called disc, and over the disc, this is the integral part of the turbine rotor. And here this is red one is called the blades, and this one is called the yellow one is called the diaphragm, where the stationary blades are installed. So where these rotary blades are subject to high RPM. Stationary plates are normally remain stationary. Diaphragm is a blades. So from here only steam will pass through this direction change. A little pressure drop will take place, and here these are the this is the rotor blades. Is subject to high centrifugal force. Centrifugal force. Now, next one is your. This one is the rotor assembly. You can see this one is the rotor assembly, and this is called the balancing drum. Because this side it is the high pressure side, and you see gradually the blade size are increasing, because this side is exhaust route side, low pressure side. So low pressure side means pressure is low, so volume will be more, and here high pressure side pressure will be high, so volume will be less. And normally high pressure to low pressure side turbine tendency will be from high pressure to low pressure side to move high pressure to low pressure sides. So to balance this, what we are doing, you see the area of the diameter of this rotor here and diameter rotor here, the difference is there. So this side cutting will nozzle, through this nozzle the steam will come here and here also, and this side, from this side here pressure will be same. But as this area is less, this area is less, this area is more, so the additional excess area, the high pressure steam will act on this side, so this will balance the low pressure rotor tendency to go to this side. So this is called the balancing drum. After balancing drum, there is a labyrinth seal is there, it will go to the gland to it will go to the stack. So due to this high unbalanced area, steam will act on this particular excess area here, low pressure side, this side, and this will force on this side, so keep the rotor in center position. And these are the guide blade carrier. You see, this is the guide blade carrier. Here only, this is called the diaphragm. On the diaphragm, the guide blades are mounted. Guide blade are mounted. This is the guide blade are mounted. So this is the stationary part, and this is the rotating part. How this level now, as the blades are very subject to very high centrifugal force, you need to be fixed on the disc through a feed tree or dovetail type connection should be there, so that due to high centrifugal force, this will not fly out. This will not fly out. So if next page slide you see, this is called the dovetail type joints. This is called the feed tree type joints. This is the D-level bulb type joints. So here this will be fixed on the grooves of the disc, so that it cannot go out. Here also the similar groove will be there on the disc of the turbine rotor. It will fix into the grooves, so this will not go out like this. So these are the connection, the types where by this the rotor blades will be mounted on the disc. You see, So this is the guide blade carrier. This is the guide blade carrier. This is the rotor. So this needs to be center because rotor should be need to be center. First, we are what we are doing. We remove all this guide blade carrier and put the rotor on the bearing housing. These are the journal bearing. Similarly, front journal bearing. This is the side is rear journal bearing. This is the balancing drum. You see, this is the balancing drum. This is the balancing drum. This is this side area. This side area. This side. The different. This side area is more than the this side area. So this will due to steam will force push the rotor in this side. So it will balance each other. But actually balance each other. But this rotor guide blade carrier, you have to do the rotor centering first. So if you put the rotor on both the journal bearings, front journal bearing and rear journal bearing, label it, and there is a previous reading is there, protocol readings is there. Once you put this rotor on journal and adjust the and do the centering, then rotor will automatically put in center position with the casing. Now with the casing, rotor will be put in center, perfectly center position with the casing, and then with the thrust bearing also, thrust bearing also. Then once we put this guide blade carrier, you have to keep the clearances of the guide blade. You see that the rotor is having the labyrinth seal here. Guide blade is also after blade, it will having the clearances with the rotor shaft. So you have to keep the gap of guide blade carrier with the rotor shaft equal. So how do you, and up and down also, how we are doing? We are using these guide blades are normally rested on the threaded cap and bush, and there is a eccentric bush is there at the bottom of this every guide blade carrier, so that you can tilt it to angular position, and to this cup here and here you can lift up and down. So when the put this guide blade carrier, leave put we have to rotate. You have to rotate the threaded cup and rotate the threaded cup. This and spherical washer. This guide blade carrier will go upside, and this labyrinth seal will touch the rotor blade, and then rotor blade. And as per the protocol, again you have to bring this rotor down, not guide blade carrier down, and through this filler gauge you can measure the gap between this rotor guide blade carrier blade to rotor shaft, and rotor blade to the guide blade carrier, so that equal clearances will be there both throughout the blade and throughout the rotor. This is the way we are doing the centering of the rotor. Then this is the call I have called you that this is the threaded cup. This is the threaded bush, and this is the cup. The cup will be placed on this threaded bush, and over it the guide blade carrier will be there. Will be resting on this cup. So once you outside there is a thread, and this will be mounted on the turbine casing. If you rotate this, rotate this, then this will move up and down, and accordingly your guide blade carrier will move up and down, and you can do the centering, maintain the equal gap of the top side of the rotor and at the bottom side of the rotor and the side of the rotor rotor. Then you can see this is the rotor centrifugal critical speed depends on the length of the supporting bearing, length of the supporting bearing. You see this, that's why we are this is the conical side. You see exhaust hood casing are conical inside. If you because we want to bring the two support close to each other, so the critical speed range will be higher side. If you increase the supporting length, then the critical speed will be lower. Then it will, the rotating RPM will be on the operator, will be inside the inside your operating range, or in during or maybe in the operating range. So that's why critical speed is there. The rotor will, if the rotor is running with critical speed, then rotor will subject to bow and high vibration will be there. So to bring down the critical, to bring to increase the your critical speed, your supporting system should be as close as possible. That's why the exhaust root are making conical, and that's so that the length between this is the front journal bearing, this is the front journal bearing, this is the rear journal bearing, so that you can put the rear journal bearing slightly inside. So length will be less. When length will be less, your critical speed will be high, and it will be more than the operating speed of the turbine of the process. And this is the thrust bearing. This is the thrust bearing. So that is the reason the conical shape has been provided in the turbine exhaust root casing. You see, this is the casing, lower half of the casing. This is the top half of the casing. This is the this one is called your steam chambers. These bolts are the casing parting plane bolt. These are high pressure. These are the very high pressure bolt, because this side high pressure is there. This side low pressure is there. So these bolt, particularly bolt, we are using this particular 4-5 bolts, or all the bolts, we are subject to high temperature, and we need to need to heat it, heat the bolt, special type of bolts, to heat it, expand it, and then tight the bolt, so that once we cool, bring the parting plane bolt cool down, then this will grip this top half and the bottom half very tightly, so that there should not be any leakage from inside to outside. Not only that, if you see the earlier configuration, you see there is some grooves are there. You see, these are the grooves provided on the turbine casing, so that the landing portion, this particular portion, two parting plane will come in contact, so that the with this the parting plane bolts. So once then only this much landing portion, pressure, much more pressure. If the pressure, the total force is distributed over these two whole length, then what will happen now? Distribution, this will subject to whole pressure, then whole force, then pressure will be less. But if if you tied this, only this, if you keep these two portion contact each other, when top half and bottom half, the pressure on this portion will not come in contact, this portion not come in contact, only this portion and this portion come in contact. So for the equal force, the pressure will be more, so there should not be any leakage on the parting plane. Not only that, you have to do the blue matching of the parting plane with the viscosite and lead paste will be there. That is, if there is any grooves are there on that will be filled with this viscosite on lead plate, and blue matching, 100% blue matching, or on a 95 to 100% blue matching is required, so that all this sitting portion will be come in contact. All the sitting portion will come in contact, so that there should not be any leakage of the steam from the inside steam to outside. This is the gland portion. Because the high pressure turbine are condensing integrating turbine, so condenser means less than atmospheric pressure. This is the condenser side, this is the high pressure side. So if we have to for steam flow also, from high pressure to low pressure, steam will go only when there is a pressure difference is there. But so you have to create a condenser vacuum. First you have to create a vacuum in the condenser. The steam whatever coming, it going to the condenser, you have to create a vacuum. So for that we have to create a ceiling. This is called the rear gland. This one is called the front gland. So what we are doing, we are introducing some steam from the, before starting we are introducing some steam here, so that it will come to the gland portion, this gland portion, it will come to this gland portion, and there will be sealing. Some steam will go inside and some steam will go outside, and vent. Once you see the vent, steam is coming from the vent, that means sealing is there, and once you see the vent on the rear side, that means sealing is there. So outside there is no chances of steam, or from here also outside there is no question of any steam to come ingress. So you can create the vacuum inside in the condenser, so that once you vacuum is there, then your steam will come inside, go to the turbine, and it will go to the condenser. But you see, there is two control valve has been provided. During running, what will happen, to the high pressure steam will come inside. From here also the steam will go to the rear side also. From high pressure steam, from here to the running condition, high pressure steam will, there is no need of giving any outside steam. From here it is through this gland, it will go to the rear gland. Suppose this pressure is high, then what will happen, this valve will close, outside valve will close, and then this valve will will open, and this will go to the condenser. But if suppose there is pressure has low, gland pressure has been come down, I mean you cannot see any vent, then what will happen? This valve will close and this valve will open, so it will maintain the sealing. It will maintain the sealing. And then another one is very important thing is there, as the area of this gland and the clearances are very less, the heat transfer will be more, particularly in this site, and there is a lot of condensate formation will be there. And once the condensate formation inside the gland and rotor is there, rotor will come in contact with the condenser, then there will be a thermal shock and rotor will can vibrate. So we have provided a drain here, we have provided you see there is provided a drain. Through this drain it will go to the condenser again, it will go to the condenser again. So there is a lot of steam during starting condition. When this one gland is cool, there is chances that there are lot of condensate is there. So that condensate need to be drained both the sides. That's why the drain provision is there, that will go either to the condenser or atmosphere. You see, this is the gland portion. You see where the sealing steam is coming. Sealing steam is coming. Once the sealing steam is coming, you see the sealing supply line. From here, it will go to this side. It will come to this side. From here, it will going to this side. It will go to vent. You see here steam is coming. After this lab is seal, it is going to vent. It is going to vent, and then sealing supply, and then from here sealing here it is also going to vent, and some drains are also there. Drains is also there, this is going to drain. Similarly, in the low pressure, this is the high pressure site, and the low pressure sites also, you see the sealing steam supply is here. Here it is going to drain, and here it is, from here it is going to vent. And this one is the luval side, so that no oil should come to the steam side. So there is a it is called sealing is there. If it is a lube oil pump or lube oil or condensate is coming from this side, there is a drain. From here it will go to the drain, and oil is also should not come, but if it is come also, then also it will go to drain. This one is called the oil catcher. This is the oil catcher. This is the steam end side, this is the exhaust end side, and this is the fins with the rotor fins provided. So rotor, I have told you the 90% of the unbalance due to high pressure and low pressure, rotor is subject to going from high pressure to low pressure side. So, and rest of the axial thrust will be taken by the this thrust collar. This one called thrust bearing. This one is the thrust tilting pad thrust bearing. And not only this is the thrust collar. This will you can move the rotor thrust bearing, so that rotor center rotor axially will be actually placed, and the guide blade carrier and axial clearance of guide blade carrier with the rotor blade will be equal in both these sides. That will be taken care of by this thrust collar, as well as the some axial load is there, unbalanced axial load is there. 10% of the axial load will be taken care of by the thrust bearing. You see, this is the thrust bearing. This one is called the thrust bearing active, because normal case you see the rotor will move from high pressure to low pressure side, high pressure to low pressure side, high pressure to low pressure side. So this particular thrust bearing, this particular thrust bearing is subject to high pressure. That's why it is called active side, because rotor will try to move from high pressure to low pressure side, high pressure to steam end to coupling end. This particular thrust pad is called the active side, and this side is called non-active. When rotor normally should not come from low pressure to high pressure, but it may come during extraction and others, but this will be momentarily it may come. That's why both sides thrust bearing should be designed in such a that both side axial thrust, the thrust bearing can take the axial thrust. This thrust bearing is take the axial thrust, and this is the tilting pad, so it can save the shape of the collar, and then between the collar and the thrust pad, lube oil film will be there, so that, and this is a white metal, so there should not be any contact with this thrust pad with the collar. So with the color only, and it is subject to high temperature because rotor is subject to high steam, and this rotor will be always highly heated, and not only that, axial thrust will be there, so there is a steam heat generation will be there, that will be taken care by the thrustal lube oil, lube oil, lubricating oil, and it will going to drain, Then next is journal bearing. This will thrust bearing will take the thrust load, and journal bearing will take the radial load. This is the tilting pad radial bearing, journal bearing. Normally 5 tilting pads are there, 4 tilting pads are also there. These tilting pads are normally pivoted on pivot type. It can move all this side radially, so that radially, and its shapes are these curvature are normally slightly more than the rotor journal curvature, so it will make a oil film developed here, and to take the so that the rotor will not directly touch the white metal, and that simply just floating between the journal bearing pad and oil film. In between, oil film will be there. This will take the complete radial load. This is a tilting pad. Sometimes fixed type, when 2 lobe, 3 lobe, 4 lobe bearings are also available. That is fixed type. But here, in particular case, it is tilting type. It can tilt all the direction, from this direction and this direction. This is so that we can avoid there is a phenomena. It's called oil wheel, that can be avoided if you can use this tilting type journal bearing. But if you are using 2 lobe type journal bearing, there is a chances are there the oil wheel can take place, oil whip or oil wheel can take place. If oil wheel and oil whip take place, this particular case it will not be there because it is a tilting type, so there is no chance. But in lobe bearing, the chances are there. That's why we try to use, normally we are using for high critical high design or high pressure design turbine, tilting pad type journal bearing. These are the oil seals of both these sides, so that oil will retain inside the rotor, inside the journal bearing, and the this pad and inside the pad and these oil seals are there. So oil will be always there. If you are not using this seal, then oil will come directly to outside. So that's why the seal has been provided, and journal to this clearness is are maintaining less, so that this particular portion will always filled with the oil. Rest will go to the drain. This is the main oil pump. This is the main oil pump. This one is the main oil pump. Normally, the this to starting the turbine, we have auxiliary oil pump, because that is a motor driven auxiliary oil pump, AC power supply, motor driven oil, main oil auxiliary oil pump. Then one main oil pump will be there, that is normally normally shaft driven. Lube oil pump and auxiliary oil pump is also motor driven. And then emergency oil pump, this is these 2 pumps are mounted on the oil console. When the turbine is standstill condition, lube oil pump and auxiliary oil pump will start, and turbine will keep the turbine speed increasing. When the turbine speed will reach to the rated speed, then auxiliary oil pump will stop. Main oil pump or shaft driven main oil pump will take over and give supply to the journal portion, journal bearing, thrust bearing, not only turbine but also the other driven equipment like gearbox and compressor or pump, etc., whatever may be. And emergency oil pump means if this pump power, suppose there is a power failure, auxiliary pump is not available, then emergency oil pump, DC power driven will come in picture, and this will give to the oil to the journal portion, because turbine is very hot condition, it is remain heated. But if you during coasting down or during starting, if you coasting down, if oil is provided to the journal bearing, then there is a chances that white metal will burn out, and rotor will come in contact with the casings, and rotor will damage. That's why to establish the oil flow, main oil pump, auxiliary oil pump, and emergency oil pump are provided. Normally, due to the oil should be clean. That's why what we are doing, inlet oil line we are providing stainless steel, and outlet as it is going outside we are providing with carbon steel material. You see, this is the main oil pump, this is the auxiliary oil pump. In auxiliary, when during starting, the main oil pump is not running. At that time, auxiliary oil pump will start. You see, this is the relief valve, this is the NRV. It will pass, it will start, and from here it will go to the cooler, because to maintain the temperature of the lube oil, normally 39 to 40, 38 to 45 degrees centigrade we are maintaining. Then NRV, then filter. If there is any foreign particles are there, then filter will do, it will arrested in the filter, and then finally clean clean lube oil pump will come to the header, and from this header it will go to the journal portion. This is the turbine, this is the front journal bearing, rear journal bearing, this is the gearbox, front side of the gearbox, rear side of the gearbox, this is maybe generator or pump, whatever maybe it could maybe. Then front and rear thrust bearing is also there. It will go to the drain and go to the oil tank, go to the tank again. But once this turbine reach to the rated RPM, then slightly higher than this RPM, then this pressure will be slightly high. Automatically this will release the load. You can stop it, but keep it in open condition. Stop the lube oil pump, auxiliary oil pump, keep it on running, keep it on standstill condition. Then through this MOP, motor air driven, shaft driven, again that's in relief valve, then NRV, it will go to the cooler, NRV again, and then filter, again it will come to the header, ring header, and from here it is going to, through this bearing, it will go into the tank. And these are MOP, main oil pump. We are not using any, and these are the pumps. Normally you are using positive displacement pump, because we need, for each rotation we need some oil flow should be there. If it is a, suppose if you are using a centrifugal pump, then valve is closed condition, then no oil will flow. But if it is a positive displacement pump, oil flow will always be there. And here if it is pressure is more, then this suppose the release valve is not working properly, then some oil will drain. But that's why MOP, the emergency oil pump, we are not providing any relief valve, so that when it is running, oil flow must be established to the bearing. There must be stability bearing. And this emergency oil pump is required only when the auxiliary oil pump is not running, MOP is not running, MOP is not running, decoupled condition, or it is not, power is not supply or decoupled condition. Then this auxiliary oil, this emergency oil pump should run, and it will at least give to oil to the bearing portion. But suppose it is normally DC or DC power driven. This is auxiliary power, this is DC power, direct current. But suppose this DC power is also not available, then at that time what will happen? We are providing one overhead lube oil system. Overhead lube oil system. This is normally kept at around 10 to 15 meter, so that the at bearing level, bearing housing journal portion, pressure will be around 1.4 to 1.5. Pressure is available. From during normal running condition, what will happen? Some oil will go through this, the normal oil, suppose AOP and MOP is running. So from here, some oil will come. This valve will remain closed condition. Then for this orifice, this NRV, oil flow will take place only this direction. Through this orifice, some oil, minor oil will go to the tank, overhead tank, and from the overhead tank, this valve will, this is a drain line, it will normally closed condition. So through this outlet, it will go to the drain, to the drain condition, but it will remain always in the full volume. And this volume of this tank is such that the coasting down period plus 45 minutes oil should be available, so that during running, when the turbine is tripped, coasting down window till full speed to zero speed, it will take 10 to 5 to 6 minutes or something like that. During that period, oil should be available, and then rest of the time also, when turbine is in burning gear, at that time also, as the turbine is subject to high temperature, that also going to give the oil supply to the to this oil. From here it will come to, when this pump is not running, this pump is not running, this pump is not running, this tank is full. So during this condition, oil will pass through this valve will remain closed, here, this will going to the lube oil header, and lube oil header, it will come to different bearings and then come to oil tank. This is the heater we are provided to maintain the temperature, I think, and this is the cooler to maintain the the heater normally required in winter season when oil temperature is very less. At that time you can keep the heater on so the temperature remain 38 to 42 degrees centigrade. And if the temperature is more, then you can keep this cooler in operation. So friends, I think I have clear the different parts used for uh, turbine system running, as well as the turbine internal parts, stationary blade, then moving blades, disc and diaphragms, thrust collar, journal bearings, and balancing drums, the connections, etc. So these are very important parts of a turbine. These are basic. Is required for any turbine running to any turbines. Apart from this, also some ejector systems are also there. Emergency stop valves is also there. Extraction stop valves is also there. There are so many other items are also available. But these are the basic items I have discussed here. If you go through this, your idea about turbine parts will be totally clear. And if clear, and if you have any doubt, you can call me back by my phone or email. Thank you very much.